Every structure you've built in this course is a line. The array, a line of slots. The string, a line of bytes. The linked list, a line of nodes. Stacks and queues, lines with rules about which end you may touch. Even last lesson's hash table is an array wearing a converter, a line with a clever doorman. And a line is the wrong shape, twice over. First, look at your actual data. Open DevTools on any web page. Elements inside elements inside elements. Your file system, folders inside folders. A JSON payload, values nested in values. The world keeps handing you hierarchy, and we keep flattening it. Second, the want list from last lesson. Keep every key sorted and answer in logarithmic time. Lesson 1 told you where log comes from, the only place it ever comes from. Having. And to have, you need a fork in the road, a place where one comparison can send you one way or the other. A line has no left or right. So today, the structure that does. And here's the good news. You already own every part. A node from Lesson 5, recursion from Lesson 9, a queue from Lesson 6. We're just going to wire them together. Here's the tree this whole lesson walks. 6 values, 4 at the top, 9 and 2 below it, 7 and 1 under the 9, 8 under the 2. Deliberately not in any sorted arrangement. Hold that suspicion. It pays off next lesson. Now the vocabulary, straight off the picture. 4 is the root, the one node nothing points to, the entry point. And yes, computer science trees grow downward. 9 and 2 are the children of 4, and 4 is their parent. Every node except the root has exactly one parent. That single rule is what makes this a tree and not a general graph. No merging branches, no cycles, one path from the root to anywhere. 7, 1, and 8 have no children. Those are the leaves. The height is the longest path from root to leaf, counted in edges. Here, 2. And now the word that matters most. Look at 9, with 7 and 1 under it. That cluster is a complete, self-sufficient tree in its own right, a subtree. Every node is the root of its own subtree. Sounds like trivia. It's about to become the engine of everything. Last term. Binary means at most 2 children, a left and a right. Real trees, the file system, the DOM, have any number. Binary is the teaching case, and everything generalizes. Lesson 9. Made a promise. Trees are the data structure that is nesting, and recursion would be the native language there. Time to cache it, because the caching happens in the definition. A binary tree is either empty, or a node holding a value, a left subtree, and a right subtree. Read that again. The definition refers to itself, twice. Every structure before this one was defined by arrangement, slots in a row, nodes in a chain. This one is defined the way recursive functions are written. A base case, the empty tree, and a self-reference, the 2 subtrees. Recursion stops being a technique you apply to a problem and becomes the shape of the data itself. And in memory, nothing new at all. Lesson 5's node was a value plus 1 next pointer. This node is a value plus 2, a linked list node with 2 nexts. Null plays the empty tree, exactly like it played end of chain. That's the entire structural inventory, 2 pointers per node and a definition that refers to itself. The payoff of a recursive definition is that algorithms fall out of it, almost passively. What's the height of a tree? Transcribe the definition. If the tree is empty, -1. That's a convention, chosen so a single lonely node gets height 0. Otherwise, the tree is 1 edge taller than its taller subtree. 1 plus the max of height of left and height of right. 3 lines. Check them against Lesson 9's 2 rules. Base case, the empty tree, handled first. Progress. Both calls descend into strictly smaller subtrees, and the tree has a bottom. So take the leap of faith. Trust the 2 smaller answers. On our tree, the subtree under 9 has height 1. The subtree under 2, height 1. 1 plus the max of 1 and 1, 2. Correct. And we never traced a frame. Counting nodes, same move. Empty is 0. Otherwise, 1 plus count of left plus count of right. Handle empty. Trust the two smaller answers. Combine. Nearly every tree algorithm you will ever write is that 3-line skeleton wearing different combine logic. That's not a coincidence. It's the definition echoing back. Now the marquee. A traversal visits every node exactly once, the tree's version of looping over an array, and its order in, no way around in visits. But something genuinely new is here. A line has one sensible order, front to back. A tree, at every single node, has 3 pieces of business: the node itself, the left subtree, the right subtree. Keep the subtrees in left then right order, and the only question is when you handle the node. Before both subtrees, between them, or after both. 3 answers, 3 traversals, plus a 4th that refuses the question entirely. Same 6-node tree for all 4. Watch the sequences change. First, preorder. Node, left, right, visit 4. Then the entire left subtree, 9, 7, 1. Then the right, 2, 8. 4, 9, 7, 1, 2, 8. Parents before children, top down. That's the order for any job where a child needs its parent to exist first. Copying a tree, you create a node before you can attach children to it. Serializing one to disk, same logic. And you've seen it printed 100 times. The tree command, that indented directory listing. Each folder before its contents. That output is a preorder walk. Second order, left, node, right. Drain the entire left subtree, then the node, then the right. On our tree, 7 comes first, the deepest left, then 9, then 1. That finishes everything under 9, so now 4. Then the right side. 2 has no left child, so 2, then 8. 7, 9, 1, 4, 2, 8. Look at that output. It's nothing. No story, no pattern. An arbitrary shuffle of the same 6 values. And that's honest. On a tree with no rule about where values live, the in-between order has nothing to say. Remember this one anyway. Of the 4 walks, this is the one to file away. Because next lesson, this exact walk does something almost magical. And that's all I'll say. Third, left, right, node. Both subtrees fully handled before the node itself. 719-824. The root goes last. Children before parents. Bottom up. The order for any job where the parent's answer is built from the children's answers. And here's the thing. You've already run one. Lesson 9. The directory size function. The do walk. The size of a folder is the sizes of everything inside it, computed first, then summed at the parent. That file system walk was a postorder traversal. Now it has its name. Same story for freeing a tree in a language with manual memory. Free the children before the parent, because the parent holds the only pointers to them. Delete it first, and everything below is orphaned. Leaked. Postorder isn't a stylistic preference there. The problem leaves you exactly one legal order. The showpiece for bottom-up is the expression tree. Take 3 plus 4 times 2. That expression is a tree. Times at the root, plus on its left, with 3 and 4 as children, 2 on its right. Operators are the internal nodes, numbers are the leaves, and the parentheses you type are just construction instructions. Now evaluate it. You cannot apply the times until both operands are known, and the left operand is itself an expression. So, down the left, 3, 4. Apply the plus, 7. Right side, 2. Now the times has what it needs. 7 times 2, 14. The values became available in exactly post order. And this is not a toy. Your compiler parses source code into an abstract syntax tree, an AST. Expressions containing expressions, Lesson 9's nesting. Evaluating that tree, type checking it, folding constants at build time, post-order walks, every one of them. Because an expression's type depends on its children's types. Every time a type checker tells you A plus B is a string, it computed A and B first, bottom up. The fourth traversal refuses to pick a branch at all. It visits by floors, the root, then everything at depth 1, then depth 2, 4, then 9, 2, then 7, 1, 8. Level order. And look at what runs it. No recursion, no stack. This one runs on Lesson 6's queue. In queue, the root, then loop. Dequeue a node, visit it. In queue, its children. Trace it. The queue holds 4. Dequeue 4, visit. In queue 9 and 2. Dequeue 9, visit. In queue 7 and 1. The queue now holds 2, 7, 1. Dequeue 2, visit. In queue 8. Then 7, 1, 8 come off in order. Leaves. They add nothing. First in, first out is the level ordering. Children join the back of the line, so everything on the current floor gets served before anything deeper. Lesson 6 promised this queue would one day run a search that explores level by level. This is the first payment. The full version, breadth-first search over graphs, is Lesson 17. So the family splits clean. 3 walks are depth first. Commit to a branch, follow it to the bottom. They run on a stack. 1 is breadth first, sweep wide. It runs on a queue. Hold that split. Lesson 9 left you a correspondence. Any recursion is a loop plus an explicit stack, because the call stack was just a stack all along. Apply it to preorder. Make a stack, push the root, loop, pop a node, visit it, push its right child, then its left. Right first, so left pops first, and the left subtree finishes before the right. Same output as the recursion, frame for frame. Now, put that function next to level order from the last scene. Look at them. Same skeleton, line for line. Seed the container with the root. Loop until it's empty. Take one out, visit it, put its children in. The only difference is the container. Swap the queue for a stack, and breadth first becomes depth first. The stack hoards the newest thing and digs. The queue serves the oldest thing and sweeps. The container isn't an implementation detail of the traversal. The container is the traversal. Lesson 17 will make this exact statement about searching entire graphs. You've now seen it first on 6 nodes. One bill left to read, and Lesson 9 taught you how. Recursion depth is frames, frames are memory, and for a traversal, the maximum depth is the height of the tree. A reasonably bushy tree with 1,000,000 nodes is about 20 levels deep. That's Lesson 1's halving arithmetic run in reverse. Each level roughly doubles the node count. 20 frames? Nothing. But check the definition again, because nothing in it forces bushy. A tree where every node has only a right child is a perfectly legal binary tree. And it's a linked list in a costume. Height n, recursion depth n. Everything priced per height quietly becomes order n. Hold that thought. It is next lesson's whole subject. One representation note before we land. Everything today is nodes and pointers, so traversals pay Lesson 2's toll. Every child link is a pointer chase, and scattered nodes commute instead of stream. There is one famous family of trees that escapes. Pack a complete tree, every level full, into a plain array, and index arithmetic replaces the pointers entirely. That trick is how Lesson 15 builds the heap. 2 lessons away. Now look up from the 6 nodes. You touched all of this today. Every query selector call walks the DOM's element tree, depth first. Document order is preorder. Prettier parses your file into a syntax tree, walks it, and prints it back. ESLint hands you the walk directly. A lint rule fires on entering a node and on exiting it, pre and post, 2 visits on the same walk. Even find has a dash depth flag whose entire job is switching its walk from preorder to postorder, because rm-r cannot delete a folder before its contents. But notice what never happened today. We never found anything fast. Ask whether 8 is in the tree, and nothing beats visiting nodes until you bump into it. Order in, exactly what the line cost. The forks are all there, a left and a right at every node, each able to discard half the structure per comparison. They're just not wired to anything, because values can live anywhere. Next lesson, one rule about where values may live. And every fork becomes binary search's halving step, alive inside a linked structure. The sorted, logarithmic structure last lesson asked for. And the walk I told you to remember? Fires, binary search trees, and the degenerate case. That's next.